This module is a discussion of the KEQ of reactions that are not in water. So these are non-aqueous acid-base reactions. First of all, some comments on solvents. Why do we use solvents? Well, solvents can dissolve reagents. Not all reagents dissolve in all solvents. And so we need to have these dissolve so they can meet. Solvents can also participate in catalysis of reactions by lowering the energy of transition states so they can make reactions go faster depending on solvents. We're going to learn more about this later. Solvents can dissipate heat, so if a reaction is exothermic, you might have a large concentration of heat if you don't use solvents. If you use solvents, it can dissipate the heat into the bulk solvent, and that'll make the reaction much more controlled. So what about aqueous solvents in reactions? Well, aqueous solvents dissolve very polar reagents. We would have trouble getting some of these reagents to dissolve in organic solvents. We'll see that a little bit more later on. Also important about aqueous reactions is that water can accept or donate protons. So they act like acids and like bases, and that's sometimes good and that's sometimes not good. What about non-aqueous solvents? Well, what are these? These are going to be solvents like ethers and esters and amides. You don't need to be worried about that so much. So at this point, just understand that these are non-aqueous solvents for reactions. And so we're going to need non-aqueous solvents if we're going to use strong acids or bases. If we use strong bases, we don't want those bases to pull a proton from water, which can act like an acid. If we're using strong acids, we don't want the lone pair of water to act like a base and associate with those acids. And so we don't always want to use aqueous solvents. Often we want to use non-aqueous solvents. So let's talk about a non-aqueous acid-base reaction. So the reaction below is of the ethanol, which is the alcohol, with ammonia, and that's going to give us the alkoxide and ammonium. So here the ammonia on the left is grabbing a proton from the alcohol, and the electrons are remaining on the oxygen. I've drawn the arrows because I always want you to think about describing these in terms of arrows. So this is a non-aqueous reaction. I haven't indicated what the solvent is, but let's just say it's not water. So there's not a water to act like a base in there. But I want you to note there are acids on both sides of the equilibrium. The alcohol is giving up its proton when we start, the alcohol is giving up its proton to go towards the right. And the ammonia is grabbing a proton to make the ammonium. You can think about it this way as well. If you look on the right side of the equation, that's striving to go towards the left side. So the ammonium is trying to give up its proton to alkoxide. That's the anion of the sodium after it's lost its proton. That ammonia wants to give up its proton and push the reaction to the left. So we have two acids competing to give up their proton. We have the alcohol trying to give up this proton to push the reaction to the right, and we have the ammonium trying to lose a proton, give it up to the alkoxide, and move the reaction to the left. The prediction you're going to make is that the stronger acid will give up its proton. So in order for you to assess this, you have to be able to say, oh, we need to be able to identify the acids and their pKa's. So the acid on the left is the alcohol. It's losing its proton to go to the right. The acid on the right is ammonium. It's losing its proton and trying to move the reaction to the left. Those are the two acids. Which is the stronger acid? Well, the stronger acid has the lower pKa, so that's ammonium. The stronger acid is going to give up its proton. That's the prediction that you make. So that ammonium is going to push the reaction to the left, and the left side of the reaction is what's going to be favored because the ammonium is a stronger acid. So in other words, we use the pKa's to say which side is going to be favored. Because this reaction is favored to the left, the KEQ is going to be less than 1. And you need to be very familiar with both of those. It's favored to the left, KEQ is going to be less than 1. That's saying exactly the same thing. Here's another example. We have phenol on the left side in red. We have hydride as the base. I'm giving you examples that you're going to see throughout the course of the semester. And so this is a base that we're going to see later on. A hydrogen with a pair of electrons is a hydride. It's going to grab the proton from the phenol to make the phenolate that's on the right side. That's the compound with the O minus and H2. And if you think about it from the point of view of the right side of the expression, while wanting to move towards the left of the equilibrium, we have H2 loses a proton to become hydride as it goes from the right-hand side to the left-hand side. So we have two acids again. We have the phenol, pKa is around 10, and we have H2, pKa of around 35. So phenol is a much stronger acid, so this one is going to be favored to the right. And so it's going to be very strongly favored because there's a big difference in acidities. Those acidities are measured with pKa's, and so the phenol is a much stronger acid. By the way, note that phenol in one of the earlier sections we talked about it being a much stronger acid than regular alcohols. You should know that regular alcohols like the ethanol in the first example, pKa is around 16. This pKa is around 10, and you should recognize that it is much more acidic because the conjugate base is stabilized by factors that you should be able to identify. So this is partly how they're connected. If I had asked you what the pKa's of the alcohol and the hydrogen, the H2 are, for the alcohol, if you would have told me before now 16, I'd be okay with that. But this particular one is a much stronger acid than regular alcohols because of the stability of the conjugate base. So let's also not simply estimate or rather predict which side is favored, left or right. Let's talk now about how much they're favored. And that's an issue of the quantitative measure of a KEQ. The bigger the KEQ is, the more it's favored to the right. The smaller the KEQ is, the more it's favored to the left because of the definition of KEQ. So here's how we're going to estimate quantitatively estimate the KEQ. Step number one, we're going to identify the acids. So the acids are on the left side, it's the alkyne. It's a terminal alkyne because we have a CH on the alkyne. It's at the end of a carbon chain. And on the right side, the acid is going to be the ammonia. That ammonia is losing a proton as it pushes to the left side of the expression. So the two acids are the alkyne and the ammonia. And the pKa's of those, that's what we're going to need in order to identify which is the stronger acid. The pKa of the acid on the left, the alkyne, is 25. The pKa of the acid on the right, which is the ammonia, is 38. The acid with pKa of 25, the alkyne, is a much stronger acid, and so this reaction is going to be favored to the right. That stronger acid is going to lose its proton in this equilibrium, so the reaction is favored to the right. So now we know which side is favored. We're favored to the right. Now we need to know how much. Here we're going to talk about the quantitative measure of the estimate of the KEQ. And so what we're going to do is take 10 to the difference. The KEQ is going to be 10 to the difference between these two pKa's. So this is 10 to the 13th is that difference. Now we need to be able to say, well, is that a plus 13 or minus 13? We've already said the KEQ is favored to the right. So that means that the exponent of the 10 for that KEQ is going to have to be positive. For the reaction to be favored to the right, that is the KEQ greater than 1, that exponent has to be a positive number rather than a negative number. And so the exponent of the sign is positive because it's favored to the right. The estimate of the KEQ is going to be 10 to the 13th. If this had been favored to the left, we would say that the exponent should have been negative. So we use the fact that we've analyzed which direction is favored to give us the sign of the exponent of the estimated KEQ. So up on the top reaction, I show you the mechanism with arrows. Know how to do those arrows. That's going to be very important. Know how to assess both the favored direction of an equilibrium that's not in water, an acid-base equilibrium that's not in water, and the KEQ of that equilibrium. So let's give a couple of other quick examples that are going to be from other chapters that are going to be important to us. We can have an alkene act like a base and pull a proton from HCl. This is a non-aqueous acid-base equilibrium. The alkene grabs the proton and becomes a carbocation. It's a carbon with a cation on it, and we have the Cl minus left over. You should know how to draw those arrows. I shouldn't have to show you this, but do practice this a lot. You're going to need it desperately over the course of the year. If we're going into the reverse direction, you should be able to draw those arrows as well. By now, those arrows you should be able to draw just based on what the starting materials and products are. So the pKa of the acid on the left is -7. The pKa of the acid on the right, we don't know what the pKa of that acid is. But what you should be able to say is that carbocation is very unstable because that carbon with the plus charge in it has a charge. That's not a good thing. It's also that carbon doesn't have an octet. That's not a good thing. So let's assume that it's less than 0 or it's 0, the pKa of that particular acid. So it's a pretty strong acid. Well, the pK of the HCl is still much stronger, and so this reaction is going to be favored to the right. And if we estimate that the pKa of that proton is 0, then the KEQ is going to be 10 to the plus 7. In the third example, we could have another phenol, and this time we have a stronger base than we saw the last time. We have potassium tertiary butoxide, KOTBU. Some students in previous years call that KOTBU. We're going to see that base a lot. But in any case, that OTBU minus grabs the proton from the alcohol, and that the counterion for that O minus that's left over is K plus. The pKa's of the two acids are 10 and 18. Again, the phenol, with the acid on the left, that's much more acidic than you'd estimate based on what you memorize. pK of that is 10 rather than 16. The acid on the right side is less acidic than you would guess based on that, based on what you've memorized. The pK of that is 18. This has to do with stabilities of conjugate bases, but I won't say anything more about that other than you memorized essentially some averages or some ballpark figures, and we're going to learn how to be more specific about this later on. But in any case, the pKa of the acid on the left is stronger, so this reaction is going to be favored to the right. That stronger acid is going to want to give up its proton. And so the difference between the two pKa's is 8, and so the KEQ of this reaction is 10 to the 8th. And in the final example, we have an enolate alkylate. This is going to be from an enolate alkylation, and this is going to be chapter 13 in these visual presentations. So the reaction is the ester on the left is going to lose a proton. The most acidic proton on that ester has a pKa of around 20. We're going to treat this with potassium hydroxide. So OH minus is going to be the base, and we're going to get the two products on the right hand side. The two acids are the ester. We're going to call that the alpha proton because it is alpha to the carbonyl of that substrate, pK of 20. pKa of the alcohol on the right is 15.5. So the stronger acid is on the right side. So this reaction is going to be favored on the left. The stronger acid is going to give up its proton, which means the KEQ is going to be less than 1. And the difference between these two is 4.5. I'll just call that 5. So the KEQ is going to be approximately 10 to the minus 5. So let me give you a summary here. Acid-base reactions occur in water and in non-aqueous solvent. Under non-aqueous conditions, two acids are competing to give up their protons. And when they do this, we're going to use the pKa's in order to determine which side is going to be favored. The stronger acid, that is the acid with the lower pKa, is going to give up its proton. If the reaction is favored to the right, the KEQ then, by definition, is greater than 1. And if the reaction is favored to the left, the KEQ is going to be less than 1. And we're going to use the pKa's to estimate the KEQ of the non-aqueous acid-base reactions. And the KEQ is going to be 10 to the difference between the pKa's. We're going to assign the exponent a plus or a minus based on whether the direction for the reaction is favored to the right, that's going to be plus, or is favored to the left, that's going to be minus.